And fill in the Lewis symbols for sodium and chlorine. And nitrogen. So far, we've just been working with individual atoms. We've talked a little bit about how they bond in terms of the positive and negative charges they form, how many electrons they want to get their octets, that chart that we had on the far right board. And so what we're going to be doing now is incorporating this. When sodium meets chlorine, what do the electrons do that enables them to bond? What do those bonds look like? Sodium has how many valence electrons? 1. So there's its dot structure. How many does chlorine have? 7. Just for convenience, I'm going to leave the vacancy on this side. What kind of element is sodium? Metal or non-metal? Metal. And what metals do is they typically lose electrons. Chlorine being a non-metal, it typically gains. So if you take the sodium and the chlorine and put them together, then metal to non-metal, this is ionic bonding. This electron leaves here, goes there. You wind up with sodium as a cation that has lost its only level 3 electron. That whatever it had as valence is now gone. Now it's stable because it's got an octet interior to that. But as far as what we considered valence, that's gone. And now that electron's over here. And that gives us the chloride anion. And then what holds this particle in contact with this particle?
Twice.
Yeah. Is opposite charge attraction. But that's complete transfer from one to the other. Chlorine has an octet, that you can see. Sodium has an octet. You don't really see that, but it does. And that's what happens with metal-non-metal bonding. If we were bonding chlorine to chlorine, where each of these has 7 valence electrons, vacancy right about there, vacancy right about there. Then what happens here is not transfer of electrons from one to the other, but this chlorine tries to snatch that electron, and this one tries to snatch that electron, and you end up with something like this, where a pair of these electrons are caught in that tug-of-war, perpetually oscillating back and forth between those two nuclei. That pair is what is shared. And that kind of sort of gives each chlorine an octet. When you look at Cl2 there at the bottom, for each chlorine, how many valence electrons of its very own, not shared, does each one have? 6. But they also have access to 2 through sharing, correct? And so 6 plus 2, you count these that are shared toward both atoms. So these 2 that are shared, this is 2, 4, 6 of its own, plus access to 2 more is 8. Same for the other. Is that as good as having your very own private octet, like you did over here? No. But it's still pretty good. It's one way of achieving an octet. Now, typically the way that's drawn is with a line. Or that line connecting the 2 chlorine atoms represents the pair of electrons that's involved in the sharing. This line is these 2 electrons. So when you draw the overall Lewis structure, like what we've got at the bottom, the dots are electrons that are not bonding, and the line is electrons that are bonding. And that line counts toward both atoms. So dots and dashes are the way you draw these structures. Question so far? What's the symbol for nitrogen look like? How many dots? 5. Just as important, how many vacancies? 3. So if we bond nitrogen with chlorine, then this one and this one go in to form a bond. Does that make chlorine stable? Yeah, because chlorine now has 8. Is nitrogen stable? No, it's not. It didn't have an octet before. It's got, what, 6 now, 4 of its own plus access to 2. That's still not an octet. And so if you're bonding nitrogen with chlorine, then really, I guess, one chlorine needs to work on this spot, another one works here, and another one works here. And so what you end up with is something like this. Where in each of these bonds, the nitrogen contributes 1 to get 1. These 3 locations on the nitrogen are available for bonding. And so with each of those forming a bond, this is the proportions that you would have to have for nitrogen and chlorine to bond and be stable. Do you see how that comes out of Lewis dot symbols? When you think back to that chart that was over on the right, nitrogen, we said, preferred to have 3 bonds. And chlorine, we said, prefers to have 1 bond. And that's exactly what you've got in the structure, correct? Now, those bond numbers that were listed there were not absolute. They're not always going to be that. Nitrogen won't always be 3 bonds. But it prefers to be 3, and it's more stable if it's 3. And so, if each atom has an octet, and in here they do, each chlorine has 6 of its own plus 2 through sharing, that's 8. The nitrogen has 2 of its own and 6 through sharing, that's 8. Everybody's got their octet, everybody's got their preferred number of bonds, then you know you've got something stable. That's the criteria you want to think about. And we'll talk more about that as we go through a few more complex structures. But if you're trying to evaluate whether it's stable or not, you look for octets and you look for preferred number of bonds. And if you are correct on both counts, then you know it's stable. Questions so far? All right. Now, this is a highly haphazard way of doing these. It's very visual and it works fine for things that are small. But you need something a little bit more systematic when you get to bigger structures. And so what you've got on this page, rules for drawing Lewis structures, we're going to talk about these and go through these. And practice these on the structures that you've got boxed in below. Rule number 1. When you're figuring out the general backbone of the molecule, who is bonded to who, the central atom is going to be the atom that has the least electronegativity. The lowest electronegativity atom is going to be in the center. Look at the periodic table. Look at nitrogen and chlorine. Which one is more electronegative? Chlorine. So if chlorine is more electronegative, nitrogen is less electronegative. That explains why the nitrogen is here surrounded by the chlorines, right? It's the nitrogen that's in the center. The atom of lowest electronegativity is going to be the central atom. Now it does tell you there's an exception. Anybody want to guess who the exception is? Hydrogen. And the reason for that is that hydrogen, with its one valence electron, hydrogen is only capable of forming one bond. And whoever is in the center has to have multiple bonds in multiple directions. And since hydrogen can only form the one bond, it can never be in the center. It's got to be hanging off the perimeter somewhere, because it can only have the one bond. Even though hydrogen has a very low electronegativity, it will never be in the center. It's just not possible. Number 2, count up your valence electrons. And you do that based on the periodic table, based on those Roman numerals that you've got for the A columns, the S&P blocks. Everybody in column 3A has 3 valence electrons, etc. You total all those up. Number 3, bond the other atoms to the central atom. Each line, each bond representing 2 electrons. Then you place other electrons as lone pairs meaning ones that are not bonded. Rule 3 is where you put in the bond, and 4 is where you put in electrons that are not bonded. And you place them in as lone pairs to fill the octets. And start with the perimeter atoms, the outer atoms. Because those are the atoms with higher electronegativity, they have dibs on the electrons. So I'm going to put this chart back up here. You don't need to copy this down because it's already in your notes. But just so you don't have to flip pages. Now I'm going to put the parts of that chart that are relevant right now. We're going to draw out nitrogen trichloride again, but using these rules instead of being quite so visual about it. This is the formula. Rule number 1. Least electronegative atom is going to be in the center. That would be the nitrogen, and the chlorines are out surrounding it. Rule number 2. Count up your valence electrons, the total valence electrons in the structure. How many valence electrons does nitrogen have to work with? 5. and each chlorine has 7. So total, that's 26. 26 valence electrons that we have to account for in the structure. Rule number 3 is putting in bonds to connect the perimeter atoms to the center. That would require 3 bonds. And since each bond is a pair of electrons, then that means we've already placed 6 of our 26 electrons, right? So if there's 26 valence electrons, and 6 of those are bonding, then that kind of implies that the other 20 are not bonding. That's your only options. They're either bonding or they're not. So if 6 of these are bonding, the other 20 are not, and we place those by filling up the perimeter atoms first. So right now, the way it's drawn, this chlorine only has 2. So 2, 4, 6, and that would fill up this chlorine at 8, correct? So placing these other 20, that's 2, 4, 6, that chlorine is full. 8, 10, 12, 14, 16, 18, and all the chlorines are full. 19 and 20 would go in the nitrogen. You're always placing them in pairs, correct?
Where did you get the 6? Is that from chlorine?
The 6 bonding electrons, that was from connecting these 3 atoms into the center. The formula tells you there's 3 chlorines, and they have to be bonded, right? And so just drawing a line to represent the bond, and each of those lines is 2 electrons. So that's 2, 4, 6 that are needed just to build the backbone of the molecule. So those 6 are bonding and the rest of them aren't. That's how we make the differentiation of that 26, how many are bonding and how many aren't. And this would be your finished structure. Each chlorine has 6 of its own and access to 2 through sharing. Whoops, that's not your finished structure. It's almost your finished structure. Now it's finished structure. The nitrogen has 2 of its own and access to 6 through sharing. Does everybody have an octet? Yes. Does everybody have their preferred number of bonds? Yes. So that ought to be a pretty stable compound. And it is. Do you see how this information fits with that chart that's on your right? Chlorine is right below fluorine, so it's going to behave like that. We use these to set up this tabulation. We use these when we were placing the electrons, and then we use these at the end to kind of evaluate if we were where we were supposed to be. Question with that? Next structure is H2O. Rule number 1, least electronegative atom goes in the center unless it's hydrogen. So I guess that means oxygen's in the center by default, right? Rule number 2, count up the valence electrons. How many does hydrogen contribute? 1. Oxygen, 6. So total, that's 8 valence electrons that we have to account for in the structure. Rule number 3 is drawing in the bonds, connecting the hydrogens to the oxygen is going to be 4 bonding electrons. And if 4 of the 8 are bonding, then the other 4 are not bonding. And we place those starting on the perimeter, filling things up to their octet. So let's start with the hydrogen. How many electrons are on this hydrogen right now the way it's drawn? 2. Does it need more? No, because 2 is its octet, right? We're not filling, it's terminology here, we're not filling them up to 8. We're filling them up to whatever their octet is. And for hydrogen, that's 2. So this hydrogen's fine, this hydrogen's fine, your perimeter atoms are fine. There's 4 more to go. We put them on the oxygen. And now compare that to your chart. Hydrogen has 2 electrons, that's its octet. Oxygen has 8 electrons, that's its octet. Preferred number of bonds, 1 for hydrogen, that looks good. 2 for oxygen, that looks good. And that would be your finished structure. Do you see how this works? Once we get good at this, then we're going to start looking at things like polarity and bond angles and shape. Which things are water soluble and which things are not. You can predict all that based on these drawings. We got to work our way up to that. Right now we got to get good at the drawings. But is there any question about this drawing? Yes?
Can you explain the octet? Like how you related to that again?
We're trying to make sure that each one has its octet of electrons. And so this one bond here counts as 2 electrons, and that means the hydrogen's full already. We're not going to put any more on here, because that would be going beyond its octet. So you're filling up the atoms to reach their octets. Do this one on your own. And this is what you should do. Count your dots, count your bonds, make sure everybody's got what they're supposed to have. Once you have your drawing, you run it through that chart. You check your octets and you check your preferred number of bonds.
So we shouldn't really put it in that triangular shape, right?
I do that out of habit, but because really when you get three-dimensional, it's going to be kind of like that. But Lewis structures are not meant to show shape. It's a step that you go through in order to figure out shape. And so if you put them kind of like this, that's just as good. The important thing is the dots and dashes and having those correct. Question about this. All right, next one is carbon dioxide. Least electronegative atom goes in the center. Tabulating the valence electrons that are to be accounted for in the structure. Connecting the oxygens into the central carbon. There's 12 more to go. So 2, 4, 6, that fills up that oxygen. 8, 10, 12, that fills up that oxygen. And that accounts for all of our electrons, correct? All right. Now run that through your chart. Octets. The oxygens are octeted, I guess, but the carbon's not. Preferred number of bonds? None of them. That's not your finished structure, but that is as close to the finished structure as rules 1, 2, 3, and 4 are going to get you. All right. Next page, rule 5. Sometimes what happens, and this is something that you have to do visually because this little formula is not going to predict it for you. But sometimes what will happen is in order to finish out the octets and give atoms their preferred number of bonds, then an atom will take a pair of its electrons and fold that in to make an extra bond. So if this oxygen takes 2 electrons of its own and makes a new bond out of that, and this one does the same, look how that changes your structure. Now does everybody have an octet? Yes. Now does everybody have their preferred number of bonds? Yes. Right? This kind of folding in kind of thing is pretty much, not exclusively, but pretty much, this is an oxygen rule. Sometimes nitrogen will do it. In very, very rare cases, somebody else, like maybe sulfur. But for the most part, think of this for oxygen. You do rules 1, 2, 3, and 4, and then you look suspiciously at your oxygens, because oxygen will find a way to get a second bond. It's not a matter of will it fold in, it's going to fold in. The question is what happens as a result, because oxygen will get its second bond. This is your finished structure. We did rules 1, 2, 3, and 4 just like we were supposed to, and then we look at the oxygens. and the possibility of them folding in pairs of electrons to make it more stable. And you see how that made it more stable. It's not just a matter of octets. It's also that preferred number of bonds that you have to look at. Now, in the little square where you've drawn CO2, it's got a little symbol there to mark it as being especially important. So I'm going to copy it over here. And as we go through some others, we're going to compare back to CO2. Because there are others that will be CO2-like in their behavior and structure. So that one's marked as a reference point. Do this one on your right. And don't skip rule number 1. Did anybody come in and not get their exam? Did you get your exam?
Yeah.
You got it? No. You did not get it. Anybody else? This is step 1. Just because it's written with oxygen in the middle doesn't mean it's physically built with oxygen in the middle. Least electronegative goes in the middle, and that would be nitrogen. So that's your backbone. That's step 1. That's rule number 1. How many electrons are there to be placed? How many? 18. 18 valence electrons in this structure. Four of those are involved in bonding, which means the other 14 are not. And placing those starting out on the perimeter. 2, 4, 6 fills up the oxygen's octet. 8, 10, 12 fills up the chlorine's octet. There's still 2 more to go. Those would go on nitrogen. And that's the end of Rule 4. This is what you should have at the end of Rule 4, and we're not done yet. But a question about getting to this point. If there is, please ask. Are you okay getting to this point? All right. Rule 5. What happens?
You fold one from oxygen.
Fold one pair from oxygen, that makes an additional bond. Because the way it is at the end of Rule 4, you got a couple of problems. One, nitrogen doesn't have an octet. Also, oxygen doesn't have its preferred number of bonds, and nitrogen doesn't have its preferred number of bonds, right? So that's 3 problems you got with that structure. But when this folds in a pair of electrons, it takes care of all those problems.